Okay, so hi everyone. Today I'll be presenting my final project on for the course Introduction to System Engineering, and my topic is on securing and optimizing modern supply chains through a system engineering approach. Yeah. So let's begin by acknowledging the fact. We know that the global supply chains are more fragile than ever. So from natural disasters and cyber attacks to trade disputes and shifting policies. And any distribution anywhere can cause ripple effects across the entire chain. So many organizations still treat supply chains as isolated units, but in reality, they are deeply interconnected ecosystems. So with the rise of technologies like IoT tracking and AI forecasting, we've certainly gained speed and precision, but also introduced a new vulnerabilities. So the central challenge becomes how can we enhance efficiency without sacrificing resilience? Okay, this presentation explores how systems thinking helps us redesign supply chains to be more adaptive, more secure, and more reliable, even in volatile conditions. Next, modern supply chains are incredibly complex. They stretch across countries and industries, connecting raw materials, manufacturing, logistics, and delivery. So to cut costs, many firms adopt lean strategies, which reduce inventory buffers and increase responsiveness. But here's the catch. Lean systems leave little room for error. A cyber attack, a delayed shipment, or even a policy change can throw the entire system off balance. So Chef and Rice in 2005 argued that resilience isn't just about backup plans. It's about real-time visibility and intelligent planning. Mm. To manage this complexity, systems engineering offers a useful lens. Instead of optimizing isolated parts, it maps how procurement, production, logistic, and data all interact. We use tools like IDEF0 modeling and FMEA to visualize dependencies and find potential failure points. Cybersecurity has become another critical concern. A single weak link, like an outdated ERP system or under-secured vendor, can expose the entire network to a ransomware or data breaches. Emerging technologies like blockchain and IoT promise better traceability and real-time tracking, but they're not silver bullets. Challenges like high costs, integration issues, and data ownership concerns slow down adoption. So no one solution is enough. To truly prepare for the future, we need a cohesive strategy that combines resilience engineering, cybersecurity framework, and emerging technologies, but all integrated through the system thinking. Now let's move into one of the most critical parts of the supply chain life cycle, the engineering development system stage. This is where we go from abstract ideas to real testable systems, like hardware, software, security, logistics. Everything has to be engineered, aligned, and integrated. So it's about concepts to reality. This is where we go from it's an iterative process. At every step, engineers, designers, IT teams, and stakeholders work together to ensure that we build meets not just functional goals, but also performance, security, and adaptability targets. So we start by breaking the supply chains into subsystems, each one representing a different layer of system. The first one is physical layer. Second one is digital layer. Third one is control layer. And the fourth one is governance. For the physical layer, includes warehouse, truck, sensors, and something else. And digital layer includes inventory database, ERPs, and something else. And in control layers, there are data boards, dashboards, AI monitoring. And in governance layer, there are compliance and access control and something else. So we model the interfaces between these layers using standards like SysML or REST APIs, making sure everything works together, even across vendors. So before we touch any hardware, we run digital twins of warehouse. And also we simulate what if cases, like a port shutdown or cyber attack. And also we model logistic flows and propagation. So this helps us catch design flaws early and save cost. Then we design the real-world components, uh, which includes warehouse layouts, sensor development, and also telematics, fleet telematics with GPS, fuel, or maintenance tracking. We also plan for power redundancy and remote networking using mesh systems. All of this ensure we have a reliable, visible logistic, even in harsh conditions. So on the digital side, uh, we build ERP systems, um, real-time dashboards and data pipelines. And also we use blockchain for supplier verification and also develop APIs that speak a common language across systems. So we use CI or CD pipelines to test deploy code safely so update can roll out with low risk. Also, security is not added later. It's designed from the start. Um, we use strive threat modeling and also encrypt the data. And also, we set up like RBAC plus MFA for access control. And also test everything through the penetrating testing, red teaming, and incident simulations. So we track key metrics like MTTD and MTTC to measure how quickly threats are detected and contained. So after development, we integrate and test the entire system. Load test for performance, latency test for data transmission, resilient test for failover handling, and A/B testing between old and new systems. So we begin with pilot rollouts in a limited area to gather real feedback before scaling up. We also document everything, from system architecture to maintenance steps. Training is role specific. Warehouse works to get UI workthroughs and checklists. Admins get diagnostic uh, and simulations. We even use VR simulations to train teams in real warehouse settings. This also helps non-technical stakeholders trust the system and adopt it confidently. So transition and planning risk mitigation. Finally, before the full launch, we build fallback strategies, and also the go, no-go criteria, and also the risk register and approval checklist. All these steps make sure we're ready not just to launch, but to respond if anything fails. So in short, engineering development isn't just about building. It's about designing, testing, securing, aligning, and preparing for the real world. It bridges the vision with an execution. Now that we've built an integrated system, the post-development stage is where everything meets reality. This isn't just a handover, it's the beginning of the continuous cycle, monitoring how the systems performs, adjusting it based on the real-world behavior, and evolving it with future needs. So we don't go live all at once. We use the phrase rollout. First, a pilot development deployment for a small group, then a soft launch, gradually scaling, and finally, full development across the organization. Each stage includes configuring cloud networks, registering devices, migrating data, and verifying everything works. We keep cybersecurity teams in the loop throughout. If something goes wrong, we patch or roll back using containerization tools like Kubernetes or something else. And once developed, we track key metrics in real time. Um, so for logistics, things like inventory turnover and delivery accuracy. For security, we monitor intrusions, attempts, and response times. And for systems, we watch for latency and packet loss. Tools like Prometheus and SCADA helps visualize this. We also perform acceptance testing and post-launch reviews to ensure it's working on the ground. So no systems works if people don't know how to use it. We provide multi-layered training from basic tasks to advanced data analysis. These materials are tailored by role, operators, managers, cybersecurity staffs. They each get what they need. We also support training through LMS modules, instructor-led sessions, and even VR simulations in complex environments. Feedback from these trainings helps us improve continuously. This stage is all about listening. We collect feedbacks, sprints, and updates. We collect input from users, the system itself, and also IoT analytics. That data feeds into the improvement sprints. Things like refining interfaces or tuning forecasting algorithms. But before applying changes live, we test them in our digital twin environment. That way, we avoid surprises. And next, we focus on maintenance. This includes updating firmware, optimizing database, recalibrating sensors, and testing disaster recovery plans. Predictive algorithms helps us fix problems before they happen. And automated CI or CD pipelines let us deploy updates smoothly. We often secure long-term support contracts with hardware and platform vendors to keep everything running. And the compliance never ends. We keep detailed audit logs, sometimes backed by blockchain, uh, and go through regular third-party audits to meet standards like ISO 280 or a GDPR or something else. Governance meetings are held regularly to respond to new laws, revise data policies, and review cross-border risk. Supply chains don't stand still. We plan for scale and change. We add new users or devices. We integrate new tools. We adjust process after merging or market shifts. So we could we use cloud auto-scaling, microservices, and API-based design to make this smooth. Scenario planning, like what if a port closes, like something else, um, helps us keep us ready. We also watch for technical debt and plan when to refactor. And finally, we take a big picture view. Are we hitting ROI targets? Or are we aligning with company strategies like reducing carbon emissions or expanding to new regions? We even plan end of life for outdated systems to keep the architecture clean. So this phase is where engineering becomes strategy. So the post-development stage ensures that our system isn't just delivered, it's alive, it's optimized, governed, maintained, and continuously adapted. And it proves that great systems aren't finished when they're launched. That's just where the real work begins. So now let's shift gears and talk about the biggest roadblocks. Even with a solid engineering plan, real-world supply chain systems are incredibly hard to design, hard to implement, and maintain. These challenges go way beyond tech. They include human behavior, legal systems, and global uncertainty. So, challenge equals to tech and people and policy. So, modern supply chains are massive. They span continents, time zones, and thousands of partners. The more connected we get, the more fragile the system becomes. A single ERP glitch or custom delay can cause a chain reaction. We deal with this by using systems modeling, like System ML, IDF0, which help us break down the supply chains into parts and visualize how failures might spread. So also, legacy systems are everywhere. Some warehouse still rely on spreadsheets. Others use 20 years old ERP software without APIs. This creates huge headaches when you try to connect cloud platforms or IoT devices. The key problems include no data standards, slow middleware, untested connections, and we address this with custom middleware, modular upgrades, and, and dual system transitions. Every stakeholder wants different things. Suppliers want predictability, retailers want agility, logistics teams want efficiency, and often these goals conflict. So we use stakeholder matrices, QFD charts, and performance dashboards to reconcile these tensions. But we also need legal agreements and shared KPIs to keep everyone aligned. Here's a major pain point, cybersecurity. As we connect more devices and systems, we also expose more attack surface. One weak vendor can bring down the whole chain. So the key tactics include zero trust architecture or secure encryption, continuous monitoring and red teaming and pen tests. So security equals to built in, not bolt on. We're not just dealing with tech rules. We're dealing with legal ones, and they're different everywhere. Um, like GDPR in Europe, CCPA in California, data localization in China, and exporters laws in the US. So we manage this with blockchain locks, jurisdictions aware access control, and regular audits. If we fail, the cost isn't just fines, it's shutdown or lost trust. And another challenge is how do you scale the pivot when the world changes overnight? Let's think COVID lockdowns or sudden damage surges like Black Friday or geopolitical events that block routes. Rigid systems can't adapt. That's why we use microservices, containerization, and scenario planning. And even the best systems can fail if people don't use it. Some fear job loss, others miss old shortcuts, some just don't trust the system. So to address this, we integrate uh, gamified training, UX testing, and feedback channels directly into rollout plans. Change management is a core engineering task. Finally, the business case isn't always clear. How do you measure the value of a cyber attack that didn't happen, or the ROI of better reputation? So we use tools like um, Monte Carlo simulations, TCO plus VOR matrices, or industry benchmark. These help justify long-term investment in systems that are preventive, not reactive. All these challenges, technical, regulatory, human, are why systems engineering matters. It gives us the structure, the discipline, and the tools to tackle complexity head on and to keep adapting when things don't go as planned. So let's now wrap up by reviewing what we've learned from the entire system engineering life cycle, from planning to development, deployment, to post-launch management. At every step, the key lesson is we can't eliminate complexity, but we can engineer around it. Modern supply chains are evolving fast. They're more digital, more fragile, and more exposed than ever. That's why this project took a life cycle system-based approach to design, secure, and optimize supply chains operations. Supply chains aren't just trucks, warehouses, and servers. They're interconnected systems, physical, digital, and organizational. This mindset helps us model ripple effects, identify systemic weak points, uh, and evaluate resilience, not just cost and speed, cost or speed. We also learned that modularity equals to survival. When supply chains evolve, new tools, new policies, new crises, we need to plug in things in, not rebuild from scratch. That's why we built with microservices, APIs, and containerizations. And also, security must be built in, not bolted on. Security isn't something you sprinkle on at the end. We integrated security from day one, zero trust encryption, threat modeling, secure APIs. And this protected not just the system, but the entire business network. A perfectly engineered system can still fall if people don't trust it or use it. That's why we engaged stakeholders from the start, including mapped competing priorities, hosted testing workshops, and shared dashboards for transparency. Digital twins, simulations, and what if models paid off early. We used them to fine-tune sensors placement and role-based access compliance workflows. This saved time, reduced errors, and avoided costly fix later on. As the system grows, rules must grow with it. Old school manual audits don't scale, so we built blockchain-based traceability, automated risk sense, adaptive compliance systems. The system didn't end at launch. We had to monitor performance, patch vulnerabilities, plan for version upgrades, refactoring, and even sunsetting. So this is where engineering becomes strategy. So, what would we recommend for future projects? Um, uh, the first one is embed system thinking early. We used modeling tools and collaborative plannings from the start, and also design for evolution. We assume change, we use modularity to enable it. And also also operationalize resilience is also important. Use simulation backups and redundancy as a standard practice. And maybe something else. Yeah. So in the end, this project wasn't just about tools, text, and dashboards. It was about building a live system, ones that resilient under pressure, secure by designing, scalable for the future, and also trusted by its users. And that ultimately is what system engineering is all about. And thank you so much for listening to my presentation. And this is my final project for the course Introduction to Systems Engineering. Thank you so much.